This global population trendline shows that by the year 2050, half of the entire human population will be affected by myopia. Myopia, commonly known as nearsightedness, occurs when distant objects appear completely out of focus, while close-up vision remains clear. For decades, people have treated this as a minor optical glitch. Put on a pair of glasses, and the problem seems solved. Take them off, and the world dissolves back into a heavy blur. Myopia is a physical deformation of the human eye. This elongation is a biological response to the specific conditions of modern life. We spend days staring at screens, living in dense urban environments, and isolating ourselves from natural sunlight. These specific environmental triggers actively disrupt the biological signals that dictate how a child's eye develops. The eyeball itself physically elongates. Left unchecked, this structural stretching carries massive risks for permanent blindness later in life. To understand why the eye stretches, we have to look at the biological baseline of a healthy emmetropic eye, an eye where the optical power and physical length are perfectly matched. Parallel light rays enter a developing eye, converging precisely on the retina. A biological feedback loop, emmetropization, calibrates this. As the eye expands, this loop constantly adjusts the cornea and lens, keeping the focal point perfectly locked onto the retina. Perfect vision relies entirely on this delicate biological calibration. When modern habits scramble the input signals, the entire system fails. Excessive near-work and indoor isolation cause what clinicians call retinal defocus signals. The feedback loop breaks down, confusing the outer white layer of the eye, the sclera, and triggering unchecked tissue remodeling. Comparing a normal 23mm eye to axial myopia, the eyeball stretches past 26 millimeters, causing the focal point to fall short of the retina. In refractive myopia, the length remains normal, but the cornea dramatically bulges forward, also forcing light to converge prematurely. Because the primary form of this disease actively stretches the entire organ, the condition is rarely static. It is a process of continuous structural degradation. Clinicians classify the severity of this degradation by measuring the refractive error in negative diopters. It progresses from low myopia, progressing to moderate, and hitting the danger zone. High myopia, defined as a prescription worse than -6.00 diopters, or an axial length exceeding 26.5 millimeters. This medical illustration reveals the severe consequences of extreme stretching. In high or pathologic myopia, the scleral tissue pulls so tightly that the eye structure physically tears. This leads to internal bleeding, structural scarring known as posterior staphyloma, and the atrophy of the macula. A highly myopic eye is a structurally compromised eye. Extreme elongation turns the routine need for corrective lenses into a high-risk scenario for retinal detachment and irreversible vision loss. Viewing myopia as a structural disease forces a completely different approach to diagnosis. Doctors are moving beyond subjective tests, like the traditional Snellen eye chart, where patients simply read letters on a wall, and utilizing precision measurement tools called ocular biometry. Looking at this simulated biometry scan, you can see how the machine maps the eyeball from front to back. It calculates the precise antero-posterior length in millimeters. Tracking that physical distance over time is the single most critical predictor of future tissue failure. For children, clinicians pair this with cycloplegic refraction. By administering specific eye drops, they temporarily freeze the eye muscles to rule out false measurements caused by accommodation spasms, which happens when the eye strains so hard it mimics nearsightedness. Obtaining the exact physical dimensions of the eye allows medicine to actively control the progression of the disease, moving from temporary correction to long-term structural management. Childhood is the critical window for these medical interventions. Because the scleral tissue is still soft and actively growing, its dangerous elongation can actually be slowed. Modern progression control defenses include low-dose atropine drops, rigid ortho-K lenses worn overnight to gently reshape the cornea, and soft contact lenses with specialized peripheral defocus designs. But the single most crucial prescription is entirely environmental. Children require a strict minimum of 2 hours of outdoor natural light per day to properly reset their biological growth signals. Once eye growth stabilizes in adulthood, management shifts toward permanent surgical options. Depending on the severity, this includes laser procedures like LASIK and SMILE, or implanting phakic intraocular lenses directly into the eye. The 2050 projection is a significant public health challenge, but it is manageable. Regular physical screening and proactive early intervention can protect the architecture of the eye before structural damage occurs.